let's move further to really understand where we get the signal in MRI. Okay, so far what we have built is the overall process involved. We talked about how you put it in a static magnetic field. You allow time, it will all start to align itself in the Z direction, the convention that we are using. And of course, when you have it, it is not just going to align, it is going to have a alarmer frequency, it is going to precess around, right? So your magnetization vector has a net magnetization in the Z direction. With no further action, the components in the other XY direction is going to be random. So you're going to have net magnetization only in the Z direction. In the XY direction, it will all sum to 0 just because of the effect of only static magnetic field. Now, in the next step that you see, if we can introduce another rotating magnetic field, then we will be able to manipulate this magnetization vector so that in the XY also you will start to make them in phase, right? Therefore, you will have magnetization vector component in the XY direction as well. And then here the steps talk about what happens if you switch off the your static magnetic field is still there. You switch off the additional excitation rotating magnetic field. Once you do that, what will happen? In the XY direction, it will start to become random, right? So it will start to relax in the XY plane, and also in the Z direction, it will start to align, get back to its equilibrium value, right? So there will be an increase in the Z direction so that it gets to the maximum possible equilibrium value. In the XY direction, the signal relaxes to 0. So the rate at which the time constant involved, we refer to T1, T2. We'll talk about this again, understand this further. So now what we need to do is all this intuitive understanding of magnetization vector changing with the time, right? In the presence of static magnetic field and the manipulation with the rotational magnetic field. We need to put them in form of equation. The motion of this magnetization vector, we know this motion. Qualitatively, we have described this. But we need to mathematically describe the equation that governs this motion. Okay, so that is what we'll attempt to do in the next 10-15 minutes. Of course, that motion has to be somehow related to the signal that comes out. So we talked about magnetization vector capturing the physics of the signal, but what do we measure? That we have not really talked about, which will be the discussion point. After we develop the mathematical framework, the equation, then we will conclude with the signal that is measured. So to start with, you have the magnetization field that you are putting in the static magnetic field. So you have microscopic, you put them in. So first thing that we know is this magnetization vector is a function of R and T. That is, where is this volume coming from, and it is varying with the time. So it's a function of R and T. We talked about the relationship between these microscopic level. We talked about the spin, angular momentum, and the magnetization vector. Remember, we used a mu or the microscopic spin. So we had a relationship there. Therefore, naturally, if you take a volume, right, then you have a net magnetization vector, capital M, that has to be related to the bulk angular momentum. You have angular momentum due to individual nuclei. So if you take a volume, you have many of them. So there is a bulk angular momentum, capital J, is related to your net magnetization vector, capital M, using M is equal to gamma J, the same analogy that we had with the microspin. Mu is equal to gamma angular momentum of individual spin. Same thing is hold here. We call capital J as the bulk angular momentum. So now what we are interested is, if you take a sample, right? We take a sample volume, we will call that as the volume element, right? Voxel. So when you have the small sample volume, then we will focus our attention on that. Then we can reduce this M as a function of space and T. We can reduce it to M of T because we will pretend that now we are interested in a small volume and there is no much variation in that. So you take a small volume, we call that as M of T. I mean, We'll just worry about how does that small volume, the magnetization vector from that small volume is going to behave with time. Can we describe the motion equation of the magnetization vector using a small sample volume, right? And this equation was derived by Bloch, which was called as Bloch equations, which we'll try to put together. So starting with what we know, right? When you have m of t, it experiences a torque. So we have the magnetization vector, net magnetization vector. If it is experiencing, if you have an external magnetic field, then this magnetization vector is going to experience a torque, which is given by tau is equal to m cross b. Very similar to what you have with the gravitational field. I'll show an example of the top, and maybe that will make you recall the material that would have covered in your engineering mechanics when you talk about gyroscopes. Okay, so you have a torque which is m cross b. So now we know torque is related to the angular momentum. Again, this you should have you will know inside out. Maybe if I tease you and talk about the linear counterpart, this all will make sense. So what is linear counterpart? Force is equal to mass into acceleration. What is acceleration? Is rate of change of velocity. So mass into dv by dt. So you can have d by dt of mv is the linear force, linear motion, right? So not the angular motion that we have here. So linear motion. So d by dt of mv is the linear force. So force governing the linear motion. So what is mv? mv is mass into velocity, which is your linear momentum. So rate of change of linear momentum gives you your force governing the linear motion. Analogously, you will have angular momentum. Rate of change of angular momentum will give you the rotational force, which is your torque, right? So it's all makes sense. Go brush your basics. So tau is equal to dj by dt. So we can actually fuse. The previous slide we had m is equal to gamma j. Now we are having tau is equal to m cross b. So we can eliminate j here by combining these two. So we can have d by dt of m of t equal to gamma m of t cross b of t. Okay, so we have just combined m is equal to gamma j and tau is equal to m cross b, and tau is related to j by the dou by dou t. So we have fused these three and eliminated j. So now what you have is, this is valid for short time. Again, this is a very troublesome notation. Short time we really do not know. I mean, for now we will say short time means they're not in relation to the time constant. Remember we talked about T1, T2. So somewhere we'll have to define this short time, which will become clear when we progress further. But for a moment we will assume that this is valid, provided the time instances that we are talking about is short. So using the right hand thumb rule, we can say m is rotating around z if it is not aligned with the z direction. So this is the z direction. It is rotating around z direction, right? This is what we have so far. So now let's essentially describe this with little more detail. So you have now what we are talking about is describing this precision due to static field, right? So we'll have to now reduce the general equation to the context that we have. So we'll say the B of t is nothing but, we'll pretend is your static field, and let us say that you are starting at some angle alpha, arbitrary angle alpha. So now what happens to your motion equation? D by dt of m of t is gamma m of t cross b of t is what we had. Now I am saying B of t is actually nothing but your static magnetic field, which is B naught. So B of t becomes B naught, and let's say that your magnetization vector when you started, right, at 0, time equal to 0, was aligned at some arbitrary angle alpha with respect to your z. So when you put this together, and we can actually tease the magnetization vector into different components. So you can have m x of t m y of t and m z of t, right, in terms of the variables that you see here. Of course, your phi is your phase in the xy direction. So this is your magnetization vector of each of the components, split into each of the component. So magnitude of your m naught here is nothing but the magnitude of m vector at time equal to 0. Phi is arbitrary. So this governs, this is the motion equation that tells that the magnetization vector is precessing around in the z direction. Okay, this is very similar to uh, in the gravitational field counterpart, your top experiment, right? So when you have the top, it is rotating, so you have axis of rotation, but then there is a gravitation that is trying to bring it to the floor. So this is your top. If you keep the top without angular momentum, what is going to happen? If I place my top here without any angular momentum, no spin, what will happen? It will fall down. So gravity is trying to pull it this way. So therefore, what you have is, you have an angular momentum. It is rotating about this axis, so rotating about this point. Okay, if you want to really read the material, go read about rotation about a point in your engineering mechanics syllabus. So it is rotating about this point. When you don't have angular momentum, gravity is pulling it in this direction, so your rotation moment is going to be in this direction, but it is going to spin about the axis. There is going to be angular moment in the direction of spin. So essentially what is happening, because of that, it is moving around in this direction, right? That is exactly what you have here. It is precessing around the z direction. So now what we will do is, we'll go further. We want to understand the signal. So we now understood the magnetization moment, how it is changing with the time. We are able to describe it. We need to now proceed further to measure this quantity. Okay, that is what we are going to build. So magnetization vector, we have split it into mx, my, mz, but you will notice that it is profitable that there are two instead of working with 3 variables, we could work with 2 variables by making this intuition that we already talk about mz of t, so that is your z direction. So you should retain your mz of t, because that is what we have built. But then when it comes to the other mx and my, instead of having mx and my separately as 2 variables, we could actually talk about the component on the floor. Okay, that will in other words, one we will call it as longitudinal magnetization, which is the z direction. The other we will call as transverse magnetization, which is mx of t, that is the vector, magnetization vector on the floor, which of course has mx and my, my. It's a complex variable, and of course the phase of that is given by tan inverse of my by mx. But notice carefully what we have done. We have split it into 2 components. One is the z direction, which we call as longitudinal magnetization. The other is the magnetization in the floor. Okay. You will notice that the z will not change rapidly. No change. Longitudinal magnetization, if you have your z direction, it will come to the equilibrium value, for example, after wait for several times. In the static magnetic field, the z is achieved, the net magnetization in z direction. Whereas here in the xy, what is happening? This is the frequency, it is rotating rapidly, right? So your xy is changing. The projection on the floor is spinning fast. Whereas on the z direction, it is not changing much. So one component, the transverse magnetization, is rotating rapidly, whereas the z direction is not changing. Okay, so that is a very key component that we want to understand. So now let's get into the NMR signal. So we have understood the magnetization vector. It is spinning in the transverse direction. It is changing less rapidly or not changing in the z direction. Okay. So now what we want to do is we will write the transverse magnetization, which is mx of y of t, as from the previous equations that we have, right? Sin alpha e power. So this is your rotating component which has a phase it has some starting value. Sin alpha is the starting value, alpha is the some arbitrary wherever it started. So the rapidly rotating transverse magnetic field. So when you have, see, we did this when we started, we said when you have current loop, right? When the charges rotate, spin, it is like a current going in circular loop, which will give rise to your magnetic field. Now we are talking about magnetic vector rotating, right? It is rotating. So when you have a sample and the magnetic vector is rotating, then it creates a RF excitation, right? It's reciprocal, electromagnetic. So when you have magnetization vector that is rotating rapidly, then the sample is experiencing a RF excitation. So what will happen is, if you put a coil of wire outside the sample, this RF excitation will induce a voltage. So you have, initially when we were talking about the charged particles, right? Charge spinning, which is current across a loop, giving rise to magnetic field, the M vector. Now we are saying if you have a M vector that is rotating fast and you put a coil, that will induce a voltage, right? This is essentially the signal we measure. So we measure the voltage in the MRI, or in the NMR signal is essentially measured as a voltage using the Faraday's law of induction. So you have magnetization vector. We built our case understanding the meaning of this magnetization vector and what it physically signifies, right? Now we are saying, in order to measure that, if we put a coil, then this magnetization vector, right, because it is cutting it, it will induce a voltage, and this voltage will be proportional to the M vector. Okay. So how do we measure it? Simple. We use reciprocity. What do I mean by that? If I have a coil and I pass a unit current on this coil, it is going to create a magnetic field, right? That is, you apply current, you get magnetic field. Now I am saying, if you measure this, if I have magnetic field and I keep a coil, it is going to induce a current. That is reciprocal. So if we can do the forward, then I can say, if I have a magnetic field and I put a coil, this will be the voltage or the current, and then the voltage that is coming. So I can characterize this. I can have this BR, which is my receive coil. In some sense, it's calibrated. So receive coil sensitivity. Okay. So now my voltage that is induced is nothing but, you have the whole object. In the whole object, you have MR of T. You have this magnetization vector that is rapidly changing. So the rapidly changing, so dou by dou T, rapidly changing magnetization vector, right? So that, when it is captured by BR of R, that is the voltage that you are getting. So the whole voltage, the sum of all the voltages that you get from the entire object due to this rotating magnetic field cutting the coil and inducing a voltage that is proportional, is your signal. So let's take a deeper look at this. So V of T, the voltage that you measure, is going to depend on this MR comma T and your receive sensitivity. So you'll have to simplify this to make some meaningful understanding of what's happening. So this is the big picture. So now let's simplify it. First simplification will be, okay, I see this BR of R. That means the receive sensitivity is a function of spatial location. Why should it be? Let's assume that if I have a coil which is equally sensitive to all R, that is, if I apply a current, it creates a magnetic field at location R. That is how we got about this BR using the reciprocity. So we will say that whatever magnetic field, wherever it is created, it will proportionately create the corresponding voltage. Therefore, it is not dependent on where it is. If it is homogeneous, right, or it is uniform, right? We assume that BR as this reciprocity, that is, it is uniform. Then we can have just BR instead of R. It will just be BR, right? It's not it is sensitive to each location equally likely. Then you have this mr of t. Oh, so your volume, right? Mr is function of location, t is function of time. So why should we worry about that? If you take a small sample volume, so your r is at some location, you're taking a small sample volume, then we could pretend that within that sample volume there is not much change. That is, you take a sample volume and say this is homogeneous sample volume, right? Then I can get rid of this R. Okay, so what I have done is, let's assume BR of R is R, that is, it is uniform sensitivity of the coil. Then I have MR of T reducing to M of T, meaning I've taken a small volume, so it's a homogeneous volume. There is no much changes within the given volume. If that is the case, then I can write all these terms in terms of x, y, z coordinate. Now you have these vectors, right? So I'm going to split this into components and write it. So I can write longitudinal magnetization changes to slope, right? We talked about this. Longitudinal magnetization is your M along the z component. The z component is changing slow. At least we can pretend it is changing slow compared to your the other direction. So at least that much we can assume without going deeper. So essentially, we substitute all this as simplification. We can write V of t is nothing but omega naught Vs. Vs is now sample volume, not voltage. This is a very common mistake students have when you read the text. Vs is sample volume, not your voltage. Okay, so beware of that. Then you have your m naught, S sin alpha, Br, and the sign quantity. Okay, so notice now that this is your voltage that you are getting. We can make some sense of this. If you really look at it, what is this saying? You have some magnitude which is changing sinusoidally. So this is a sinusoidal signal. Not only that, you know what is the frequency of the sinusoid, right? You already see this omega naught. So essentially what you are recording is a sinusoidal signal whose frequency is also not a big deal, because you know it is omega naught. So the only big interest to us now is to understand the amplitude part of it. So your signal that you are measuring is a sinusoidal signal of a particular frequency which is low, right? There's a Larmor frequency that you are operating, and it has an amplitude. So the signal amplitude is what we need to understand a little more intuitively. So what do you measure? You measure a voltage, and that voltage, magnitude of the voltage is omega naught Vs m naught sin alpha Br. So what does this say? What do you know from before? You know something about omega naught, that is the Larmor frequency. What is the Larmor frequency? It is related, it is related to the magnetic field. You can increase the frequency by increasing the field strength. We saw this before. Likewise, what is your m naught? Oh, magnetization vector. That also can be increased by increasing the field strength. So we can already recall omega naught is gamma B naught, and m naught is this quantity B naught, gamma square, h square. Remember we talked about this. And then you had the proton density. Again, it is coming here also. More the proton density. So you can see the signal that you are recording is proportional to square of your B naught and proton density. This is very important. So now you understand, if I go from a half a Tesla machine to 1 Tesla machine, 1.5 Tesla machine, 3 Tesla machine, the signal inherently is same. My volume is same, my proton density is same. But if I increase the field strength, my signal strength goes up. Therefore, if my signal strength goes up, I can get better quality signals, right? Of course, we haven't talked about noise yet, we'll come back. But at least we are increasing the signal. But we are not increasing linearly, we are increasing it non-linearly. So if I go from 0.5 Tesla to 1.5 Tesla, it is not like I'm increasing the signal strength by 3 times. I'm increasing the signal strength by 9 times. Okay, so that is a very, very, very big advantage. So now you see the fundamental signal that you are recording in MRI, which is in voltage, is nothing but a sinusoidal signal. The strength of the signal is proportional to square of the magnetic field that you are using. Of course, if you are measuring it from a volume, if you increase the volume, right, you get more signal. But you know the challenge. Without talking much, we know the challenge. If I increase the volume, yes, I can increase by signal, but then what is happening? The resolution is going to go down, right? I can say I get this net signal from the head, which is fantastic. I'll have a lot more signal, but then I'm interested in seeing the changes within the brain. So I need some smaller volume so that I can localize better. So this is the inherent trade-off that we'll have, right? So we'll stop here. In fact, we'll just do one more before we stop, which is now what we need to do is we need to go to the next stage. Now we know the signal. In a static field, I know how to define this, I know how to measure the signal. What did we want to do? We want to make it coherent. We started with some alpha, right? Some alpha value. When will it be maximum? This voltage maximum, the magnitude. When your sine alpha is 1. What does that mean? Alpha is 90 degree. What was alpha in our thing? Oh, if your magnetization vector was on the floor, right, then you'll get the maximum signal. That is what it says. So we started some alpha as arbitrary. If you can make this alpha go to the floor, that is 90 degree, then you will get the best signal. So the idea is, how do we manipulate this alpha? We talked about apply another rotating magnetic field with the same frequency, then you can manipulate this magnetization vector. So now you see the you get that insight. So now we can manipulate the transverse component. So we need to add one more signal, one more rotating magnetic field to manipulate this alpha. Then we could get signal. So we need to build our material to add to our signal equation, the motion equation. What happens? We add additional rotating magnetic field. Right now we have simplified it for a static magnetic field and talked about motion equation for this thing. So now we need to add one more rotating magnetic field so that we can manipulate the magnetization vector. So it will become little complicated from visualization point of view if you use laboratory coordinate system, and therefore we could go for rotating frame of reference, where essentially what we are talking about is, imagine you are applying another magnetic field, right? This another magnetic field. So this is my, because of the static magnetic field, this is what my magnetization vector is doing. Now I want to apply another one, but that has to also rotate, right? Only then I can push it to the, so that is also having a frequency which is same as the Larmor frequency. To describe this, it is going to be difficult. It will be easy if I say, oh, if I sit on this, right? If I sit on this motion, then I don't care about this one. All I see is it is going to go down. So that is reference, rotating frame of reference. If you are going to sit on the reference frame, or in this case the rotating magnetic field that you are going to apply, if you are sitting on it, then you are moving with the magnetization vector. How will it remember, right? So in this frame, B1 appears stationary. Your B0 can be, you are already done, right? B0 can be ignored because B1 is already in the same Larmor frequency, so that effect is not an issue. Effect of B1 and therefore is identical to the effect of whatever we covered right now. If you sit on it, that will be the effect that you will see. I mean, it will be very mathematically you can do the transformation and come up with the rotating frame of reference m x dash y dash of t. That is the motion of the magnetization vector described with respect to rotating frame of reference x dash y dash is equivalent to your this one. Okay, this is very easily, I mean, mathematically it's very simple. It's difficult to get a grasp of it. I just have an animation that may help you understand what we are talking. Right? Intuitively, the equation that you saw is representing this. In the laboratory frame of reference, the magenta is the motion path. Right? This is how you are representing m, which is changing in time. Okay. If you do that, this is what the relaxation that you see. Whereas in the rotating frame of reference, the frame itself is, right, you're sitting on the rotating frame B1, right? The B1, you're sitting on B1. You're sitting on B1, then you don't have to worry about that rotating. So you are just looking at this. This is a two different way of viewing it. You become more familiar with it. I mean, you would have been introduced to this in several courses in different contexts. But now try to train to get an intuitive understanding of what happens when you have B1. It may be easy to visualize the effect and rotating frame of reference. Okay, instead of having the spiral, each time I show my hand, if you pretend it is rotating frame of reference, I don't have to do this. I'll just say this M is going down, M is coming up, right? That will be the easiest way to do it. So let's stop here.